Hey guys, I thought I might just step in here and do a quick example for you of a word problem that's based on the Newton's law of cooling that we talked about in class. Remember that Newton's law of cooling was a separable differential equation, and we solved it in class and came up with this. This is kind of the general solution that tells me the temperature of an object at any time t. Here's the temperature of the medium, T sub m, and then there's some constants here, and we see that there's an exponential behavior to that temperature. But I didn't get a chance to actually show you an example. The example, of course, there's a lot of words up here. It's not really calculus, though. This is just a matter of plugging in the information and trying to solve the problem. So what's the question say? An object whose temperature is 615 degrees originally is put into a 75-degree room. Okay? Actually, so that tells you right away, a 75-degree room, that tells you that the temperature of the medium is 75, because the object's being put into that room. Okay? At 4 o'clock, the object is 135 degrees, and at 5 o'clock, it's down to 95 degrees. So it's cooling off. It was 615 degrees originally, and it's cooling off closer and closer to 75 degrees. The question is, when was that object put into the room? Okay? Really the only tricky thing here is you have to decide when you're going to start your clock. In other words, this little t measures time, but when does time begin? You could say, well, it begins when the object is put into the room, except that that's what the question is asking. We don't know when the object was put into the room. So what I'm going to recommend that you do here is that you let t equal 0. You start your time when it is the earliest time where you have some known information. So I'm going to say at 4 p.m. t is equal to 0. And we're going to measure, we may as well measure t in hours. Okay? So if we do it that way, then we know that the temperature of the object at time 0, which is 4 p.m., is 135. And the temperature of the object at 5 p.m., which would be 1 hour later, right, would be 95 degrees. Okay? So we have sort of three constants here that we don't know. Of course, T sub m we now do know. Let me just put that in. 75 plus C2 e to the negative kt. So there's two constants left that I don't know, and I have two pieces of information that hopefully will help me to figure out what those constants are. So for example, let's use the first one here. If the temperature at time 0 is 135, I can put in 0 for t. And that's just going to leave me with, so t of 0 is going to be t sub m, which is 75, plus c2. Okay, and that's supposed to equal 135. Right? So from that, we can write down that c2 is equal to 60. Okay, so c2 is equal to 60. Let me go ahead and put that down so we know that now the temperature is 75 plus 60 times e to the negative kt. So this is our new representation of the temperature function with as much information as we know. Okay? Now we also know that t of 1 is equal to 95. So in other words, if I put in a 1 for t, for the time t, I should get 95. So let me just work that out. 75 plus 60 e to the negative k. I'm putting in a 1 for t here, right? Time is, little t is 1. Well, that's great because that's going to allow me to solve for k. 95 minus 75 is 20, and then I can divide by 60. That just gives me 1/3, right? So e to the negative k is equal to 1/3. Okay. And e to the negative k, there's many ways to solve this, but I mean, one way to look at it is that's really just 1 over e to the k, right? E to the negative k is just 1 over e to the k. So then you can see e to the k is equal to 3, so you just take the ln of both sides, and you get that k is equal to the ln of 3, okay? So what we have then, let's come back over here and write down the temperature function that we have. We've solved all of the constants now. 75 plus 60 e to the negative ln of 3 times t. Okay? And the question is just asking us, when was the object put into the room? Well, that'll be whenever the temperature was 615, right? So I can put 615 in right here for the temperature and solve for little t now. That's all we have to do. 615 minus 75 is 540. We take 540 and we divide it by 60 and we get 9. So 9 is equal to e to the negative ln of 3 times t. Okay? And now if you want, well, there's more than one way to do this. You can take the natural log of both sides. So the natural log of 9 is equal to, the natural log cancels the e right here. So it equals negative the natural log of 3 times t. Okay? And 9 is the same, we could think of that as 3 squared. And so when we have a squared on that ln, we can pull the power out in front like that. See, this is really just the same thing as the ln of 9. Okay, so this is equal to negative ln of 3 times t. So you can cancel the ln of 3's and you get t equals negative 2. The object was placed in the room negative 2 hours before 4 o'clock. In other words, 2 p.m. So it's a negative time. That's because it was before 4 o'clock when the object was put in the room. So 2 p.m. Okay, so there's a couple of those on the homework assignment. I just wanted to run through. There's no calculus here. This is just solving equations and messing around with logarithm and exponential functions again. But I felt it might be nice to just show you an example of that. Hopefully it helps. Let me know.